This is section 2.2, part 2. Last time we talked about the sum and difference rules for differentiation, which were, just to remind you, that the derivative of the sum or difference of functions is simply the derivative of the first function plus or minus, whichever one it happens to be, of the derivative of the second one. Okay, so that means that we can take the derivative of something like this, f of x equals x cubed minus 4x plus 5. In the first case, we're going to use the power rule and bring down the power 3 and reduce the power by 1 to 2. Then we can use the constant multiple rule and minus 4 times the derivative of the function behind it, x. The derivative of x is 1, plus the derivative of a constant is 0. And that simplifies to be 3x squared minus 4. So now all of a sudden we can find the derivative of any polynomial whatsoever, and we don't have to do that by resorting to using the definition of the derivative with that limit process that we went through right at the end of the last problem. Example B. This one, because of the way it's written, whoops. I'm going to rewrite it. A lot of times, especially when you get a lot more experience with this, you'll do a lot of this in your head, just sort of naturally. But I want to tell you what the thought process is that I'm wanting you to internalize by showing every little and talking my way through every little step. But these are actually very easy. Once you've gotten some practice, these problems, you'll do them easily in no time at all. Okay, so I'm going to rewrite that first thing as a coefficient negative 1/2 times the power of x, so that I can use the rules that I know. The rest of it's fine. And so the derivative of g prime of x, will be the constant negative 1/2 times the derivative of the power of x, so we'll bring the power down, reduce the power by 1, plus the constant 3 times, bring the old power down, times x to the reduced by 1 power, minus 2 times the derivative of x is 1. And so we get negative 2x cubed plus 9x squared minus 2. Isn't that really fast, especially compared to the limit definition that we did before? Oh my gosh. That is quite a savings in the amount of work. Okay, this one, y equals 3x squared minus x plus 1 divided by x. Now, we haven't yet talked about any kind of rule having to do with the quotient of two functions, f of x over g of x. And there is a rule for that, but in this particular case, it would be way better and way easier, as you'll see later when we do the quotient rule, to simplify this one and treat it in a straightforward fashion rather than trying to do something called the quotient rule, which we don't even know how to do yet. So this is one of those where you can take that fraction and split it. So take each term in the numerator and divide it individually by the common denominator, and then rewrite that in a more palatable form. 3x squared divided by x is going to simplify to be 3x, whose derivative is easy. X divided by x will simplify to be 1, whose derivative is easy. And 1 over x should be rewritten as x to the negative first, which, after a little bit of practice, it's also fairly easy. So, the derivative is going to be the constant 3 times the derivative of the function x, which is 1, minus the derivative of a constant is 0, plus, take the power down in front, negative 1, times x to the reduced by 1 power, that's a negative 2, and then simplify your answer, and that will simplify to be 3 minus 1 over x squared. All right, so that's looking pretty good. Now, the only thing for that one, and I'm not going to ask that you do this, but the only thing that could be done, so I'm going to write this parenthetically, is because the original problem came to us as a fraction, a ratio of two things, we might want the answer to look like that. So if I multiply the 3 by 1 in the form of x squared over x squared to get a common denominator, that will end up being 3x squared over x squared minus 1 over x squared, which will equal 3x squared minus 1 over x squared. I have two major reasons for telling you about this, is that if you're looking at a key, like for the odd problems in the back of the book there's a key, they very well may write the answer in a different form. They may write it in this form instead of the way I wrote it and where I stopped. And I'm telling you, this form that I stopped at is perfectly fine for me. So I want you to be able to realize, oh yeah, my answer might look different from what I see in a textbook key, but I'm right. The other reason is the final exam that we'll have at the end of the semester is multiple choice. And for that reason, you need to realize that although you may have stopped at 3 minus 1 over x squared, that might not be one of the choices. You may have to realize that I've rewritten the answer in a different form, and you'll have to also be looking to see if 3x squared minus 1 over x squared is perhaps the correct answer. If you don't see the 3 minus 1 over x squared, that's when you start looking for answers that are equivalent to it, which someone might call simplified. At any rate, just wanted to let you know that that's the same answer in a different form. All right, so now what I'd like for us to do is move to a trigonometric function, and let's see what we can do with that. So let's assume that our function is, let's do sine of x. Okay. So again, we don't have a derivative rule for this yet, so we're going to have to derive it using the definition of derivative, which involves using that limit of the difference quotient. Okay, so this is going to be f of x plus delta x. Since our function is sine of x, that will be sine of x plus delta x minus f of x, which is sine of x, all over delta x. Then go back and think about the pre-cal identity you learned for the sign of a sum of two things. And you should recall that that's sine of the first thing times cosine of the second thing. Keep the sign, so since that's plus, this is plus, then cosine of the first thing times sine of the second thing. Okay, that's the sine of x plus delta x. minus the sine of x all over delta x. Okay, so I'm going to, on purpose, intentionally, get the things I want together and split this up into fractions. So I'm going to kind of do a 2-for-1 here in this step. I want the sine of x stuff together. So the sine of x times cosine delta x minus the sine of x over delta x plus the cosine x part of the problem, cosine x sine of delta x all over delta x. So I intentionally split that into 2 fractions, and I move the minus sine of x up to be with the other sine thing. So you might notice in that first fraction that sine of x is a common factor. So I'm going to factor that out, which will leave cosine of delta x minus 1 all over delta x. And I'll do the same thing, cosine of x I'm going to bring out in front, and that would be multiplied by sine of delta x over delta x. All right, the next stage is to remember the property of limits is that the limit of a sum is the sum of the limits, and the limit of a product is the product of the limits. So if I use both of those rules together, this will be limit of the first thing times the limit of the second thing plus, and we start over, the limit of the first part of that product, limit of cosine x, multiplied by the limit of the second part of that product, sine of delta x over delta x. Now, there were some limits back when we were doing limits that I asked you to memorize, and this is why. Okay, so if I'm going to put a delta x in for each, put 0 in for each delta x, sine of x doesn't have any of those, so I just get back sine of x. Kind of like taking the limit of a constant. Sine of x is considered constant when it's delta x that's changing. Okay. Then this limit of cosine of something minus 1 over that something, as that something goes to 0, this is one I asked you to memorize, and that has a value of 0. And this is exactly why we needed it. And then the limit of cosine x as delta x changes is just cosine of x. And then the other one I asked you to memorize is the limit of sine of something over that something as that something goes to 0, and that answer was 1. And so when you completely simplify, you'll get cosine x. So look at where we started. F of x was sine of x. Its derivative is cosine of x. So let me write that as a rule. The derivative of sine of x with respect to x is cosine x. We could go through a very similar process, which I'm not going to spend time on right now, and we could find the derivative of cosine of x, and it would turn out to be negative sine of x. You'll just have to trust me on that one. So these are a couple of derivative rules that you need to know. Commit these to memory. Okay. All right. So let's see, what do I want to do next? We should probably do an example or two using those derivatives we just derived. Well, the first one we derived, the other one I just told you what it was. Anyway, y equals 2 sine of x is our function. Its derivative is going to be the constant times the derivative of the function. The derivative of sine of x is cosine of x. So our final answer is 2 cosine x. B. Y equals sine of x, which is divided by 2. I would rewrite this just like I would if this were x over 2. I would rewrite this as the constant 1/2 times the sine of x. So we can use that constant multiple of a function rule. The derivative of a constant times something is that constant, so 1/2 times the derivative of that function behind it, which is cosine x. And I suppose if you wanted it to look like the original, you could do this. I'm not going to say you have to. Let's make that parenthetical. So you realize I really don't care if you leave it as 1/2 times cosine x. Okay, y equals x plus cosine x Okay, so the derivative of a sum of two things is the derivative of the first plus the derivative of the second. So the derivative of x is 1 plus the derivative of cosine of x is the opposite of sine of x, which simplifies to be 1 minus sine of x. Okay, part D. Y equals cosine of x minus pi over 3 sine of x. Okay, so its derivative, the derivative of a difference is the difference of the derivatives. So it'll be the derivative of the first thing, which is negative sine of x, minus the constant, pi over 3, times the derivative of the function behind it. The derivative of sine of x is cosine of x. And that's that answer. So now let's go back and think about something we've done before. I want to review an earlier topic. So I'm going to ask you this question. Find the equation or equations, maybe more than one, of the tangent line or lines to the graph of the curve y equals x cubed minus 12x through the point (1, negative 12) not on the graph. So this is a problem slightly new. Instead of finding a tangent line to a given point on the curve, we're going to be finding a tangent line or lines that pass through another point that's not even on the curve. Let me show you what that might look like. For example, let me say I had a curve that looks like this, and I had some point not on the curve. And I said, okay, find the tangent lines to the curve that pass through that point. Well, one of them, I'm going to guess, would be something like this. And the other one might look something like this. So you can see how you can have multiple tangent lines that pass through a given point that's not on the curve. So that may be what's happening, but we definitely have a point that we're told is not on that curve, and we want the tangent lines to the curve that pass through that point. All right. So what this is reviewing, of course, is something that we talked about earlier, that we can find, or we can use the derivative to find the slope. And so that's kind of what we're reviewing now, is just make sure that that is pretty solid in your head. Since we've done it before, I'd like for you to know that you can do this. All right. So to do that, of course, we're going to need to get the slope of a line tangent to a curve. We're going to need the derivative of that curve. So y prime is 3, the old power, times x to the reduced by 1 power, 2, minus 12 times the derivative of x, which is 1. I'm going to stop writing times 1, so I don't have to write an extra bit to get that. All right, so now that we have that, we know that the tangent line will take the form, because of the point given, the tangent line will take the form of y minus negative 12, that is y plus 12, equals m, whatever the slope is, times x minus 1. So what we're going to use for that m is, of course, that m is calculated by using the derivative that we just found. That's how we'll find that slope, because it's tangent to the curve. So that has to be true about it. So if we for a minute take out the m and in its place put this formula for finding the slope, 3x squared minus 12 times x minus 1, then we could multiply those two binomials together, which would give us 3x cubed minus 3x squared minus 12x plus 12, which, if we subtract 12 from both sides to get y by itself, will leave us with y equals 3x cubed minus 3x squared minus 12x. And this tangent line, this is the tangent line, because that's where we started, was with this tangent line idea. So this is the tangent line equation. Tangent line equation intersects our curve when they are at the same place, which means that they would be equal to each other because their y values at that point would be the same. So so when the y values are the same, or in other words, equal. So I could take the y value of the line, which is 3x cubed minus 3x squared minus 12x, and set that equal to the y that is the curve's equation. That's x cubed minus 12x. That means that the tangent line will have to go through a point on the curve. Okay, so by setting these equal to each other, we're ensuring that that's going to happen. So if I subtract x cubed from both sides, because with polynomial equations, you should always try to get it equal to 0. It's kind of one of those, you better do this kind of things. And if you add 12x to both sides to get it equal to 0, the negative 12x actually disappears. So to solve a polynomial that's equal to 0, you should factor, if you can. There is a common factor of x squared, leaving 2x minus 3. So that product equals 0 when either x squared equals 0, which means x would be 0, or when 2x minus 3 is equal to 0. That is when x is 3/2. Okay, so let's deal first with 0. The slope will be f prime of 0, which is negative 12, and the equation of our line when x is 0 is y plus 12, as we started with up above to the right, equals this slope, negative 12, times x minus 1. Okay. I didn't show you the calculation. Let me back up. Not completely back up, but I kind of skipped over an answer and I didn't talk about how I got it. So I want to rectify that. How did I get that negative 12? That's what I want to address. Okay, so our derivative function was 3x squared minus 12. So that's 3 times 0 squared minus 12, which of course is the negative 12 I said earlier. I just didn't show you the calculation. Okay, then on the other hand, if x is 3/2, the slope of the line tangent to that curve will be found by substituting 3/2 into the derivative. So this will be 3 times 3/2 squared minus 12, which is negative 21/4. And so the equation of that line will be y plus 12 is equal to negative 21/4 times x minus 1. And that's the two equations of the two tangent lines to that curve that pass through the point not on the curve that's at 1, negative 12. Okay, well, another thing that derivatives can be used for, as we saw earlier, is for rates of change of one variable with respect to another. There are lots and lots of applications of rates of change in a lot of fields. For example, the rate at which people contract COVID-19, or the rate at which water is flowing into a tub, or whatever. So Here's some more examples: population growth rates, production rates, water flow rates, velocity, acceleration, all kinds of things used in the real world. One of the most common things that we use as a major example, and I think physics uses this as well, is to describe the motion of an object moving in a straight line. In such problems, it's customary to use either a horizontal or a vertical line with a designated origin to represent the line of motion. So we could have a line, let's say it's horizontal, and here's the origin, and the point is moving on the line. So let's say it starts here and goes to the left, and then gets to there, stops, and turns around and comes back, and stops, turns around and goes. Okay, you see what the problem with that is? It's really hard to see. So sometimes you'll spread that out and go something like it goes here and there. It's actually on a line, but we're spreading it out so we can kind of see it. But anyway, that's kind of an idea of the motion left to right along that line so that you can kind of visualize where it is at various times. So when we have on a line like this one, when we have movement to the right, we're going to consider that to be in the positive direction. And when we move to the left, that's going to be considered a negative direction. If it's vertical, this should make sense to you. Positive direction is up, negative direction is down, just like the x and y axes. Where are the positive x's? Where are the positive y's? Where are the negative x's? Where are the negative y's? So that should make sense. Now, the function s that gives the position, we use s, I'm not really sure where s came from, but that's the position function is s, will be a function of time. So this is what we're going to use to represent our position function, is s of t. So if over a period of time, so we have a trip somewhere, and this is time, and this variable here is distance. We're going to have over a period of time, that is from one time to another, movement from here to there. And the horizontal distance we're moving will be delta t, the change in time. And the distance we change in going from one to the other is the change in position, delta s. And the rate at which we move, if you'll recall from probably algebra 1, is rate is distance divided by time, like miles per hour as a good example. So the average velocity in going from one point to another, which remember we said that's like finding the slope of the secant, that's our average velocity. The average velocity will be the change in distance, delta s, over the change in time, delta t. Okay, so with that in mind, let's look at example number 9. A billiard ball is dropped from a height of 100 feet. The ball's height s at time t is the position function. S equals negative 16t squared plus 100. That's our position function. Where s is measured in feet, so position is measured in feet, and time is measured in seconds. T is in seconds. Okay. Find the average velocity over the given time intervals. Okay, so from time 1 to time 2. The average velocity is going to be our change in position. So where were we at time 2 minus where were we at time 1? So this change in position, by the way, is the position at the later time minus the position at the earlier time. Okay. Divided by the elapsed time, which is 2 minus 1. This delta t is b minus a. All right. So if you calculate s of 2, you'll get 36. Let's just substitute 2 into our position function. 2 squared is 4. Negative 16 times 4 is negative 64. Negative 64 plus 100 is 36. I think you can do those calculations without my help, but just thought I'd do one with you. Minus s of 1. If you substitute 1 in, you should get 84. And of course, 2 minus 1 is 1. And so we get negative 48 as an numerical part of our answer. And what are the units? Well, if position is measured in feet, this would be so many feet minus so many feet, which will give you a number of feet traversed, divided by the change in time. 2 seconds minus 1 second means that that was 1 second long. That implies that our units are going to be in feet per second. Okay. And you might get used to at this point that if there are units in the problem, your answer should have correct units. Okay. And what does that mean? Well, because the answer is negative, that means that the ball is going down. Negative is down, okay, because it's vertical motion. So that's what the negative means. And 48 feet per second is the speed, and the negative gives you the direction in the downward direction. Okay, so the velocity, remember, is assigned speed. It's a rate at which you're moving that has a sign to indicate direction. So positive would be right or up. Negative velocity or rate of change would be down or left, depending on the circumstances. Okay, we're going to do the same thing for a different time interval from time 1 to time 1.5. So it's going to look much the same. We're still finding average velocity. We're going to take the position at the ending time minus the position at the outset and divide that by the time at the end minus the time at the beginning. So if you do that substitution, S of 1.5 is 64 feet. S of 1 is still 84 feet. 1.5 minus 1 is 0.5 seconds. And so you should get negative 40. And again, the units are in feet per second. Okay, C is on the time interval from time 1 to time 1.1. Oops, ran out of room. Okay, we'll have to be creative here with making it fit. Okay, the average velocity will be position at the ending time minus the initial position over the change in time from the ending time minus the beginning time. S of 1.1 is 80.64 minus S of 1, which is still 84, divided by 0.1, and that answer ends up being negative 33.6 feet per second. Okay. So, I'm going to have to close this off and go to another file, so I will see you in the next round.